Welcome back, everybody. In this next video lesson, we're going to talk about classification. We're going to start talking about taking matter and putting it into boxes. Not literal boxes, but we're talking about classification boxes, such as if you've got a substance in front of you, you should be able to explain if it's a pure substance or a mixture. Now, if it's a pure substance, it will either be considered an element or a compound, and we'll talk about the difference between elements and compounds. As you see on the screen, elements are the most fundamental building block of nature. If you look at that chart on the wall, known as the periodic table of elements, each one of those squares represents an element of the known universe. Some are natural and some are synthetic or made by man. Now, the smallest particle that element might be broken down into is called an atom. In fact, the word atom means indivisible. And so if you take a group of pure elements and you split them up into their individual particles, those would be considered atoms, the smallest particle that retains the properties of the element. Now, what about compounds? What makes compounds pure but different from elements? Well, compounds have to have atoms that are bonded together. Whether or not those are covalent bonds or ionic bonds, it doesn't really matter. And you might have learned about ionic and covalent bonds in a previous science course, and that's great. But we will definitely dive deeper into the concepts of ionic and covalent and the differences between them in this class. But for now, we're just talking about classification. So if an atom is bonded to another atom, it might be considered a compound. Now, this compound is unique because once the bond forms, that new substance is different than the atoms that went to make it. So the compound creates its own identity that is different than the atoms that are used to make it up. For example, water, everybody knows as H2O, is made up of hydrogen and oxygen. Hydrogen alone is a gas, oxygen alone is a gas, but water at room temperature is a liquid. Let's scroll down here and see if we can explain this using a diagram or a picture. Now, I'm just going to write the word matter here at the top, and I'm going to split matter into two sides. We've got pure substances on the left, and we've got mixtures on the right. As we know, pure substances are split up into either elements or compounds. Examples of elements could be silver or gold or even lithium or carbon. All of these examples could be described in their simplest form as atoms. Now, examples of compounds are anything that's two or more particles bonded together, whether they're covalently bonded, like, for example, water, as we said already as an example, or even sodium chloride, table salt. Delicious, delightful table salt sprinkled on top of popcorn. Now, I explained earlier how water is made up of hydrogen, which is a gas, and oxygen, which is a gas, and when they bond together, they create water in the liquid form. But I'm going to use the example of sodium chloride to kind of hammer home the same idea. A compound is unique in its chemical and physical properties, unique compared to the atoms that make up that compound. Sodium, for example, is a metal, and it's rather reactive. If you ate it, you would leave severe chemical burns in your mouth. If you touch it with your fingers, it might leave severe chemical burns on your fingers. You don't want to touch sodium atoms. Now, chlorine is a gas, and if you breathe it in, you could suffocate yourself. In fact, chlorine gas was used as a chemical warfare in World War I. This is also known as mustard gas. So sodium is a super dangerous element. Chlorine is a super dangerous element. But when you combine them together, and now they're chemically bonded, sodium and chlorine lose their deadly characteristics, and sodium chloride is completely edible. It is something that we should have in our diet, at least in a little bit. But it can be harmful to you if you eat way, way, way too much of it. Now, let's go back up a little bit. What's the deal with molecules? What's a molecule? Is it a pure substance? Yeah. Is it an element? Is it a compound? Who really knows? Actually, I'm about to explain it to you. Many of you think molecules and compounds are one and the same, but I'm going to explain to you here at this time how molecules actually are a little bit like elements and a little bit like compounds. Molecules occur when you have two and only two types of elements bonded together. So, for example, if you have something like oxygen. Now, oxygen doesn't exist in just oxygen as an atom. In fact, in nature, it exists as O bonded to O. Well, that's two elements bonded together. But that acts as a pure substance. It's an element but it is a molecule. It's a molecular element. This is what we call a diatomic molecule. But let's scroll back up here. What about water? You said, hey, well, water is nothing more than just some hydrogen bonded to some oxygen. That's two types of elements bonded together. Does that mean that this compound, which is water, is also considered a molecule? And I would agree with you. Yes, water is a molecule because it's two types of elements bonded together. And specifically, and this is important, that they're bonded together in a covalent way. Noticed how I left out our friend sodium chloride here. I didn't call it a molecule, and that's because sodium chloride bonds together ionically, not in a covalent way. And the thing about ionic bonds is that ionic bonds are ionic substances, ionic compounds, make these crystals of repeated sodium chlorine, sodium chlorine, sodium chlorine, sodium chlorine, and they grow and grow and grow into these never-ending crystals. Now we break the crystals up into smaller pieces, but covalent molecules exist as an individual package, like one water molecule is one water molecule, whereas one sodium chloride compound does not exist as one just sodium chloride. It has many sodiums and chlorines repeated over and over and over again, which is why we don't consider ionically bonded substances as molecules. So let's scroll back up here and take a look at our pictures here along the right-hand side. What we have here on top is very obviously an element, a pure substance. These are just atoms. Each one of these is the smallest that it could be, the smallest particle that retains the properties of an element. Now here on the bottom, this is very obviously a compound. This has two or more substances bonded together. Now this one in the middle, and in fact the one on the bottom, would both be considered molecules. Now this is a molecular element because you see it's the same atom bonded to itself, and that is repeated. So obviously it's pure, but it's a pure elemental molecule. Where down here, this is also a molecule, but this is a pure compound molecule because it's got two different elements bonded together, which makes it a compound, but it's only two substances bonded together, which makes it a molecule. As long as we know for sure that these substances aren't bonded ionically, and I know they're not because they're individual packets. So I've got two different elements bonded together, and they're individual packets, which means that they are compounds, but they are molecules. Now let's shift gears here and talk about mixtures. A mixture is when you take two pure substances and physically combine them together. This is not a chemical combination. They're not bonded to each other. They're just simply occupying the same space in the same time. And so this is a physical combination. Each of the substances individually retain their properties. And in most cases, they're held together by those intermolecular forces or those intermolecular attractions. Now, there's basically two types of mixtures. There's some that are known as homogeneous or homogeneous, which is what we call an even distribution, where if you take a sample of that mixture, and no matter where you take the sample from, as long as it's the same composition, maybe it's like 70% one substance and 30% the other, and as long as it's the same on all parts of that mixture, then it's a homogeneous mixture. Now, the opposite of homogeneous is a heterogeneous mixture, which is an uneven distribution. Examples of homogeneous mixtures are solutions, such as things like salt water or maybe like Gatorade or soda pop. Typically, if you can't see the stuff that's dissolved, then it is a homogeneous mixture. If you can see the stuff that's mixed together, and this is a general rule which I talk about in all my chemistry courses, is that if you can see the particles, then it's not a homogeneous mixture. It must be heterogeneous if you can see the particles. But if you can't, if it appears as to be one substance, and in some cases when you just look at it, it appears to be pure, but upon further investigation, we find that it's actually two things mixed together. We just can't see them because their particles are so small. A solution is an example of a homogeneous mixture. But also alloys. Now, you might not know much about alloys, but we'll learn about them a little bit further on in this class. But alloys are basically mixtures of two or more metals together. Now, you don't mix the solid metal with the solid metal because, as you know, these would be very visible and we couldn't mix them homogeneously in their solid state. So what we do is we melt the metals down to its liquid state, then we mix them together, and then we let them reharden, and what you get is a metal alloy. Examples of some common metal alloys include white gold, which is a mixture of silver and gold, but you also have brass and bronze, and even steel is considered a metal alloy. These are all mixtures of two or more metals put together, usually melted down in their liquid state, then mixed, rehardened, and then they are now considered a metal alloy. Taking a look at the pictures here on the right-hand side of the screen, starting at the top, you can see that this is a mixture of green dots and orange dots. And because we can see the dots, we can't use the old visual test. We don't know if it's homogeneous or heterogeneous necessarily, unless it's very obvious that the particles are evenly spread out. So looking at these models, really the best way to describe these is that I know this is a mixture, and because these are individual atoms, then I just know that this is a mixture of pure elements. Now this would be a mixture of pure molecules because we've got pink bonded to pink and purple bonded to purple, and they're mixed together. And so each one of these is a molecule, and this is a mixture of molecules. Now this one is another mixture of molecules because I got pink bonded to pink, but I've got green bonded to pink. But remember, a molecule exists as one or two types of molecules bonded together, and each one of these is acting as an individual packet, and so this is a molecule and this is a molecule. And down here is another example of a mixture of maybe a molecule and an element. So we've got mixtures of molecules in these two middle pictures, but this bottom, we've got a mixture of a molecule and an element. So in summary, mixtures could be classified as either homogeneous for evenly distributed or heterogeneous for unevenly distributed. And if you can see the particles as they're mixed together, it's probably heterogeneous. But if you can't see the particles apart from one another, then it's probably homogeneous. Well, that takes care of this video lesson. Thanks for watching.